Good morning. I hope you guys have a fantastic weekend. It should be fantastic because I've not posted homework 1 yet. The homework 1 we are delayed by 1 week. So not everything. We're still going through this problem, but while going through this problem, you guys learn about factor of safety. You guys learn about boundary condition. So fundamental stuff that you should recall from 2P04. Some changes, it's okay. And then last Friday, we went to what? Shear force and bending moment equation. By the way, I had an email from Dr. Koshi that told me that last term, 41 students failed 2P04 out of 200. Out of this 41%, 41 students that failed, 15 did not take the final exam. And Dr. Koshi was very, very kind. Those getting 45 and below, he bumped to a D minus. Okay, so he's really nice. Okay, but that's where those of you who I don't know who are you in the or where are you in that category? If you're in that category, my sincere advice is drop 1 or 2 courses, focus on this one. Are we clear? Okay, this is not a straightforward course. You see one example. 3 hours, we're still dealing with it. Yes or no? Right? 3 hours that I've been paying so much money and you still do this example. Are we clear? Okay? Right. So where are we now? So last Friday, if you look at the Friday notes, and I post all this on Avenue to Learn. We have formed equation on the shear force and bending moment distribution from point A to point C. I did not do this example. We only did from where? From point B to point C. My sincere advice is I want you to look through how to do from point A to where. Calm down, don't be shy, you're late, it's okay. Okay, don't start up there. So from A to B is easy, right? B to C is the what? It's the more difficult one. As you all know, right? I also got my course evaluation back from you guys that need to fill. Thank you very much. Okay, you gave me very good advice. Okay, very good things to improve my courses. I take it to heart, and I will do that. Are we clear? Okay, I really appreciate the honesty. That's more important. Some were a bit vicious, but I'm okay with that. Okay, vicious is fine. Okay, right. So from here, what we are going to do is we are going to look. We have the thing we're going to determine. We're going to determine the shear force and bending moment constant. Okay. Some of you might ask, Eugene, why are we doing that for? Okay, what are we doing that for? So if I go back to this slide over here, hold on, where is it? I'm finding a diagram that I drew. Hold on, okay. This is the diagram. So why do we need to find that, okay? Why do we need to determine the shear force and bending moment diagram? At the end of the day, we want to know what is our stress X and also our shear what? XY. Okay, we want to know our stress X and shear XY. And this element, as you already know wait, I know I'm copying a lot of things from previous slide, but I beg your pardon, okay? Oh, no. That is ugly. Do you find that chart useful, yes or no? Yes? Do you find this chart useful? Where is it, the ugly slide? Where is it? Do you find this slide useful, yes or no? Why is it useful? You can plan for your what? Courses. What are easy and what is what? What is hard? That's the purpose, okay?
not to show which professor is lazy and who is not. That's the secondary agenda. But wait, I want to show you a slide that I did fail here. Hold on, my bad. Wait, give me, okay. So you remember this, right? You remember this. Okay, you remember this, yes or no? This is the cross section. Okay, this is a cross section of our structure. And some of you will ask me, Eugene, where is the leading element? So we know the element that we want to position is at the where? These are your what? Failure what? Region. So this element you see over there, I'm going to zoom in. This element you see over there is positioned over here. That is the position of the element. So why do we need the shear force and bending moment diagram? We know that stress X is equal to plus or minus X over Ixx multiplied by Y. So this is how we can determine our stress X, okay, in the X mode. Then we can also determine our shear XY component. Shear XY component will be Vy over Ixx Qx divided by T. Okay, so the Mx that we want to determine will be plugged into here. And the Vy that we want to determine will be plugged into here. Can you see the relationship now? Yes or no? Okay. So from here, from the previous slide, okay, moment at point B will be equal to, so I'm going back over here, moment at point B, we're going to apply the equation which correspond to this one. Okay, so V at X, so we're going to apply this equation over here. And copy, and I'm going to paste. Okay. So we are going to substitute X is equal to L. Yes or no? Because at point B, okay, at point B, X is equal to L. So if you look at this diagram, at point B, X is equal to what? Length L. If I'm going too fast, you are lost, tell me. I will slow down. Okay, we'll just keep quiet. So from here, we can find our moment at point B is equal to minus omega naught L squared over 2L plus by omega naught L over A. Cancel. Okay, squared cancel. So you have half by 1/8. So it's equal to minus 2.5. Wrong though. So it's equal to minus 3 omega naught L over 8. Okay. Now, what does omega means over here? Okay, what does omega means over here relative to the structure? So if we look at our shear force, our bending moment diagram, so if this is X, this is M. If you look at the deformation pattern, right? Positive shear, the deformation pattern is what? Smiling face, right? Negative shear, the deformation pattern is what? Is sad face. So if we look at the shear force diagram and bending moment diagram, This is the bending moment diagram. The minus 3/8, okay, is somewhere around here. Okay, in fact, positive. No, we don't use the positive for this case. We don't use the upper value because the question asks us to design based on what? X is equal to what? L, because we are at what? Point B. In a real engineering world, you might even have to look at that. Okay, later on, I will tell you in real engineering practice, what do we do? Okay, so but for this question, it tells us to determine the stress state at point where? At point B. Are you clear? Okay, for this question, it tells us to bring the stress state at point B. So from here, we know that this is equal to what? Minus, so this is positive moment. Over here, that is what? Negative moment. When that's the case, we know, when that's the case, negative moment, we know that at this point, right? At this point, stress X is under what? Tensile. And at this point, stress X is under what? Compression. Okay, why the moment of X is acting this way? So there's something it's not new, but you guys were probably aware. At the moment vector, the head of the moment vector, let me write in a different color now. The head of the moment vector is always in what? Compression. The tail end of the moment vector is always in what? In tension. Okay. So now we know, based on this diagram that so for this case, will you do tensile or compression? That's not really matter. Because why does not really matter at all? Because the distance where failure occurs, either you take positive, you take y at this value, or you take y at minus y value. The magnitude are the what? Are the same. Because the structure is what? Axis symmetry about the x-axis. I repeat again. The structure is axis symmetry, not just about the x-axis, also at the what? At the y-axis. Clear? Crystal clear? Okay? Right. So we can take either point. Okay, so from here, we also know. So let's say we're going to analyze the tensile part. Okay, we're going to focus on this point over here. Okay, we're going to focus on this. So it will be what? In tensile. Okay, so now I'm going to get a table. So we're going to get this table. And now we need to use the table. Okay, so this table, again, this is week 1. I posted this table. So we now know that we are going to determine stress X is equal to, and we know it is minus mx at point B over Ixx multiplied by point Y, right? So we know that now this minus over here is the fact that I'm not going to do minus. We're going to do tensile. It's going to be positive, okay? Because we're going to focus on the tensile bit, not the minus bit, okay? Now, this tensile bit, we know that it's going to be positive because we have already identified that we are going to focus in the what? The tensile region. I repeat again, right? The moment we just going to use the vector, I put positive over there because we know for the fact that the point that we're going to analyze is going to be what? Tension. Okay? So now when you see this, you will come out with mx at point B is equal to 3 omega naught L over A. Y, so the distance Y, so we have to focus. So the beam that we're going to use, what beam are we going to use? 23.8. Okay, so that is the beam that we're going to use. Okay, so let's focus on this beam. We're going to use this beam over here, 23.8. Here's the last one. So the next thing we are going to do is we're going to find Ixx. So Ixx is equal to what? So given to us, Ixx is equal to 42.9. Okay, so we know that this will be equal to